Section 4.3, Gauss-Jordan elimination. In this section, we are still going to be solving systems of linear equations using matrices and specifically the process of Gauss-Jordan elimination. Okay, we were introduced to that in the last section, section 4.2, and in that section, we concentrated on a system of two linear equations in two variables. Okay, so now what we're going to do in this section is increase the size of the system. Okay, so for example, in this section, we will concentrate on systems of three linear equations in three variables. Okay, that will be our concentration. We will see some other sized systems. Okay, but again, our concentration will be on three linear equations in three variables. Okay, the good news is that the process is the same. Okay, we're just doing this to larger systems. Okay, all right, so we know that in order to do this process, Gauss-Jordan elimination, okay, you have to be able to first take your system and write it in matrix form. Okay, so in example one, we're going to practice that for just a bigger system. Okay, so let's look right here under augmented matrices from systems of equations. Okay, so when dealing with larger systems of linear equations, we simply enlarge the augmented matrix to allow for more equations and more variables. Okay, so in example one, let's write the augmented matrix of the given system of linear equations. Okay, so in example one, here is your system. Okay, you can see that there are three equations here. Okay, and there are three variables. Your variables here are x1, x2, and x3. Okay, all right, so we know this is always the first step of Gauss-Jordan elimination, taking your system, transforming it into a matrix. Okay, all right, so just write down the numbers you see. Remember, when you construct the matrix, you drop the variables. Okay, all right, the first equation, there is a 3 in front of x1. There is a 4 in front of x2. You're missing x3. So remember what we learned in the last section. If you're missing a variable, you have to use a 0 as a placeholder. Okay, the vertical bar poses as the equal sign. There's a 10 on the other side. Okay, so that's how you translate the first equation into the matrix. Okay, the second equation, there is a 1 in front of x1. We're missing x2, so we put a 0. And then there's a 5 in front of x3. And there's a 15 on the other side of the equal sign. Last equation, in the third row here, okay, we are missing x1. Put a 0, okay? There is a -1 in front of x2, okay? So be careful here, okay? Don't put just a 1. Okay, the sign here is negative. This is like -1 times x2. So there's a -1 in front of x2, +1 in front of x3, and a 20 on the other side. Okay, so make sure, like you saw right here, make sure you're using the correct sign with these numbers. Okay, all right, so that's always your first step of Gauss-Jordan elimination. Okay, translating the system into matrix form. Okay, and remember what happens next. Okay, so you're going to take your first matrix and you start operating on it. Okay, you start doing those 3 row operations to try to transform the matrix. And then eventually you get to the final matrix and then you interpret the solution. And sometimes it's helpful when interpreting the solution to do the opposite, to take your matrix and translate it back into equation form. So that's what we're going to do in example 2. Okay, so in example 2, we're going to do the opposite. You get the matrix, you're going to translate it back into a system of equations. Okay, so example 2, write the system of linear equations that is represented by the augmented matrix. Assume that the variables are x1, x2, and so on. Okay, all right, so when you look at this matrix, okay, so we know this is going to represent the equal sign. These are going to be the numbers on the other side of the equal sign. And then over here, okay, we have 3 columns, okay, so that's indicating we're going to have 3 variables. All right, so this first column is going to be the numbers in front of x1. The second column is going to be numbers in front of x2. and the third column, those are going to be numbers in front of x3, okay? When you look at this, you have two rows in your matrix, okay? So that means you're going to have two equations, okay? So this is kind of our first example of in a weirdly shaped or a weirdly sized system where the number of equations does not equal the number of variables. Okay, we'll see that a couple of times in this section. It's still doable. Like in this instance, you have two equations, but three variables. Okay, it's still workable. Okay, all right, let's go ahead and translate this. All right, so the first row of the matrix, that's going to translate into -1 in front of x1, so -1 times x1, plus, there's a 5 in front of x2, so plus 5 times x2, plus there's a 2 in front of x3, so 2 times x3, that's got to equal 8, okay? And then on the second row here, there's a 4 in front of x1, so 4 times x1 plus 0 in front of x2, so 0 times x2 plus -3 in front of x3, so -3 times x3. There's a 7 on the other side of the equal sign, okay? So if you just clean that up, you're going to get -x1 plus 5x2 plus 2x3 is equal to 8. Okay, and then the second equation will be 4x1. You're going to, 0 times x2 is going to be 0. Anything times 0 is 0. Okay, so we can omit the x2. You don't have to put that. It'll be missing. Okay, and then you'll have minus 3x3 is equal to 7. Okay, so here is the system of equations that translated to. Okay. All right, so let's talk a little bit about what we do for a larger system, okay? Like I said, it's basically the same process as working with a system of two linear equations and two variables. You're just expanding the process, okay? At the bottom of page 1, I have a little blurb about something called reduced row echelon form, okay? Um, Basically, what's going to happen is, and this applied to the system of two linear equations and two variables, but we didn't call it reduced row echelon form. If you guys remember, when we were solving a system of two linear equations and two variables, okay, we set up our first matrix and then we started using row operations. And our goal was to transform the matrix into this, where you had 1, 0, 0, 1, and then you had numbers on the other side of the equal sign. Okay, that was your goal. Okay, basically, this whole blurb about reduced row echelon form, it is basically a mathy way of saying that you're trying to achieve this goal. Okay, so what happens if we're going to bump up the size of our system? Okay, so like I said, in this section, we will concentrate on three equations and three variables. Okay, our new goal, you're just going to expand it. Okay, so now you're going to have, basically what's going on here on the left side of your vertical bar, you're wanting ones on the principal diagonal. You want zeros above and below those ones. Okay, so that's what your goal will look like on the left side of the vertical line, okay? And then you'll just have numbers on the right side, okay? So you're still going to have the same type of goal, okay? You're just doing it to a bigger system, okay? So again, these two guys, okay, with if you're looking on the left side of the vertical line where you have ones on the principal diagonal and zeros everywhere else, okay, that's what you're aiming for, okay? And like I said, this reduced row echelon form is just a fancy mathematical way of saying that this is your goal. Okay, so let's read through this. I'm just going to breeze through this. I'm not holding you to know specifically what reduced row echelon form is. I just need you to know the end goal. Okay, but let's read through these four characteristics, and you can see how they really describe our goals here. Okay, so number 1. Each row consisting entirely of zeros is below any row having at least one non-zero element. Okay, so like I said, sometimes you cannot reach your goal. So if you ended up with a row consisting entirely of zeros, it needs to be at the bottom. That's all that's saying. Okay, number 2, The leftmost non-zero element in each row is a 1. The leftmost non-zero element in each row is a 1, okay? So basically that's saying if you look at each row, okay, in your goal, okay, the first non-zero number has to be a 1, okay? So if you look at the first row, first non-zero number is a 1, okay? If you look at the second row, first non-zero number is a 1. Third row, first non-zero number is a 1, okay? Number 3, all other elements in the column containing the leftmost one of a given row are zeros, okay? They call these guys the leftmost ones, okay? They're the leftmost non-zero element in each row. They, like I said, refer to that as a leftmost one, okay? And it says, number 3, all other elements in their column are zeros, okay? So that's saying you zero out above and below these ones on the principal diagonal. All right, number 4, the leftmost one in any row is to the right of the leftmost one in the row above, okay? All that's saying, okay, is that if you drop down in rows, if you go from the first row to the second row to the third row, your ones kind of cascade on the principal diagonal. This one right here has to be to the left of this one, which has to be to the left of this one. So they need to cascade down through the principal diagonal, okay? So again, I don't want you to know, I don't expect you to know the definition of reduced row echelon form, okay? All you need to know, that's fancy language for saying that if you're solving a system of linear equations using Gauss-Jordan elimination, you take your system, you stick it in matrix form, you start operating on it according to the 3 allowed row operations, and this is your goal, okay? This is the goal for a system of 2 linear equations and 2 variables. This is it for 3 linear equations and 3 variables, okay? Real quick, I want to introduce something to you. It'll come up later in this chapter, but I'm going to mention it now because you're going to hear. I'm just going to start using the word so you get used to it. Okay. In your goal, okay, when you're looking to the left of the vertical bar, okay, where your goal is to have ones on the main diagonal and then zeros everywhere else. Okay, so over here and over here. Okay, this part of the goal, that is referred to as the identity matrix. Okay, so the identity matrix is where you have ones on the main diagonal and then zeros above and below those, okay? So your goal in Gauss-Jordan elimination is to have the identity to the left of the vertical bar, okay? All right, so that's what that word means, okay? All right, if we look at the next page, okay, so page 2, okay? This entire page, there are no examples on this page, okay? This is just here for your reference. I am not going to read through this. This is, again, just summarizing the process of Gauss-Jordan elimination. Like I said, we're just increasing the size of our system, okay? But we're going to do it the same way, systematically, okay? You are, going to set up your first matrix and then you start operating using the 3 row operations, okay? Remember what those are. You're allowed to switch any 2 rows, okay? You are allowed to multiply or divide any row by a non-zero number, okay? And that has to replace that row, okay? And then the third row operation, which you use to get your zeros, okay? You're allowed to replace any row with its sum you're allowed to replace any row by taking the row and then adding to it a multiple of a different row, okay? So it's the same 3 row operations, okay? You're going to do it systematically, just with a larger system. So once you have your matrix, you're going to start in column 1. You're going to secure a 1 on the principal diagonal, okay? You usually do that by either doing row operation number 1 or number 2, okay? And then once you secure that 1 on the principal diagonal, okay, you're going to use the 3rd row operation to zero out the rest of the column, okay? Then you move on to column 2, okay? First order of business, secure a 1 on the principal diagonal, okay? Again, you're doing that by usually by multiplying or dividing the row by a non-zero number, okay? Then you use the third row operation to zero out the rest of the column. Then you move on to column 3, secure the 1 on the main diagonal, okay? Then zero out the rest of the column, okay? So it's going to be the same process, and that's all that's summarized under this whole process of Gauss-Jordan elimination, okay? Underneath this, okay, so remember when you get to the last matrix, if whether or not, you've achieved your goal or not, okay, you have to identify your solution to the system of equations. Remember, there are 3 possibilities, okay? Either you're going to get a unique solution, which means, as far as a bigger system is concerned, you're going to be able to identify your variables. So x1 is this, or x2 is that, x3 is this number, okay? You could also use x, y, and z. That's what I prefer, actually. Okay, so if there's a unique solution, you will be able to achieve your goal of the identity matrix to the left of the vertical bar, and you'll be able to specifically say what x, y, and z are. Okay, if you cannot achieve the identity on the left side of the vertical bar, that means there's either no solution or infinitely many solutions. Okay, if there's no solution, okay, remember how you identify that. Okay, if there's no solution, you're going to see in your matrix, you'll have zeros to the left. One of your rows will have zeros to the left of the vertical bar, and then you'll have some non-zero number to the right of the vertical bar. Okay, so that's telling you, if you translated it back into an equation, it wouldn't make sense, so that's no solution. Okay, the third possibility is infinitely many solutions. Okay, and remember how you identify that. Okay, at some point in the process, you will end up with a row of entirely zeros. Okay, that indicates infinitely many solutions. Okay, and you have to parameterize the solutions. Okay, because remember, that doesn't mean that every XYZ pair or triple is a solution, only specific ones. Okay, so you have to write them in a compact way. Okay, all right, so again, anytime you're solving these systems of linear equations, okay, you're either going to get one solution, a unique solution, no solution, or infinitely many. Okay. Final note before we start practicing some of this. Okay. And I'll talk more about this later in the lesson. Okay. This is important. Okay, to know. Even though each augmented matrix has a unique reduced form, the sequence of steps for transforming the matrix into reduced form is not unique. Okay. What that means is there's more than one way to do these problems, okay? You might start working the problem and you do the whole process and you might do it totally different than someone else in the class, okay? But both of you guys could be correct, okay? There are ways, like, when I started doing this in section 4.2, I wouldn't say the easiest, but the most direct way to do these problems is by, it eventually involves a fraction, okay? But there are ways to do these problems where you can avoid the fractions, okay? So the point is there's more than one way to do the Gauss-Jordan process correctly, okay? As long as you are applying the row operations correctly, okay? There's just lots of ways to get from start to finish, okay? So just because you do one thing and your neighbor might do something completely different, okay? They could both still be correct. Okay, so just keep that in mind. All right, let's start practicing this process with larger systems.